Hey guys, welcome to the last segment in chapter 3. So we just spent 2 chapters, well, 1.5 chapters, talking about electrons. So where do electrons live? What do their homes look like? How do they file into their homes? And then a little bit about what that tells us. So why in the world did we just spend all of that time talking about electrons? They tell us about properties. Okay. The name of your textbook, Structure Determines Properties. The structure of the electrons is very, very important to us. So where are those electrons at? Where are they housed? How many are available for bonding dictates everything else that we're going to talk about in this semester. So why do we care about electrons? We care about them because of their properties. Turns out that the properties of elements are rather periodic. They repeat every 8 elements or so, much like an octet does in music. So why is it so periodic? Well, it goes back to electrons. So what we're going to look at now is just a series of slides with periodic tables that are very strategically colored to help us really zone in on some important features of the periodic table. The first feature is something that I alluded to, foreshadowed, is this idea of valence electrons. So up until now, we've used electron configurations to tell us how many valence electrons an atom has. Well, it's very important that we're able to identify number of valence electrons very quickly. So when we get into the next chapters, you're not going to have time to write out the whole configuration. You're going to have to just look and know. So what we have here is a portion of the periodic table. So what they did is they took the D block out and smashed the S and the P together. So if we were to look at this periodic table, they took this whole section out right here and then just smashed these two together. Okay. What we'll see in just a minute, these are called our main group elements. And these guys are really predictable. So to determine valence electrons very quickly, you're going to look at the numbers on the top here. So this guy is group or family 1A. So everybody in this column is going to have 1 valence electron. This guy here is 2A. Everybody's going to have 2 valence electrons. So hop over that D block and go over to boron. So boron is in 13 if you just traditionally number it left to right, or 3A is kind of a different way to number it. That 13 or 3A tells me that there's 3 valence, and 4 and 5 and 6 and 7 and 8 when we get all the way to the noble gases. So those numbers on top essentially tell us how many valence electrons there are. The reason that we pull out the D block or those transition elements in the middle is, as we've talked about before, they march to the beat of their own drum. They're not as predictable. So we don't really talk about valence electrons for those guys because they do peculiar things. Okay. The other thing that this starts to predict for us is what happens when these guys form ions. So what we'll talk about in the next chapter on the next exam is these guys losing and gaining electrons. But we have the ability to at least address this topic now. So I like to introduce it now, and then I reinforce it again in the next chapter. So let's look at the electron configuration for chlorine right here. So the electron configuration for chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. According to the electron configuration and according to the periodic table, how many valence electrons does chlorine have? Yeah, it has 7 valence electrons. I'll tell you a little secret right now. there is something magical about the number 8. So in chemistry, 8 valence electrons makes that a particularly stable element. Okay. So when chlorine goes to bond with other elements, it will steal an electron and put that extra electron in a house. So it's going to take an electron from somebody else. It's going to put it into that 3p orbital. And when it does that, it's now going to have 8 valence electrons. Well, what happens if you add an extra electron to an element? If you steal an electron, what does that electron have? Yeah, it carries with it a charge, a negative charge in particular. So when chlorine adds or steals that extra electron, it's now going to be a charged particle because the number of protons and the number of electrons is not the same number anymore. So the silly way that I remember this is it steals an electron. Stealing is bad, so it has a negative charge. Well, as it turns out, so here's the properties that we were talking about. As it turns out, everybody in this family has 7 valence electrons. So everybody in this family is going to do the same thing. Everybody's going to go out and they're going to steal 1 electron. So anytime these become charged particles, they're always going to have a -1. Okay. The reason I show this and talk about it is your textbook is wanting to start memorizing these periodic trends. No. We do not memorize anything in chemistry. So I'm trying to talk you through how this happens. Okay. These guys right here, so if we look at oxygen and this whole family, how many valence electrons do they have? Yep, they're in group 16 or 6A. They have 6 valence electrons. So to get to 8, what are they going to do? Yeah, they're going to steal 2. Does stealing 1 help at all? Well, no, because if they steal 1, then they're going to be like fluorine. Fluorine doesn't even want to be like fluorine, so that's not helpful. So they're going to have to steal 2 electrons to be like the noble gas. Stealing 2 electrons is still a bad thing, so we have our negative charge. And the charge is going to be a 2- because they stole 2 electrons. And then we go over here to the 5th family. Same story. 5 valence electrons. We're going to have to steal 3 to get to 8. So we would all have a -3. Okay. So let's go to the other side of the periodic table here. Let's look at sodium. So here's the electron configuration for sodium. Okay. How many valence electrons does sodium have? Yeah, he's only got 1 valence electron. And what would make him happy? What would make him stable? Yeah, 8 valence electrons, 8 electrons in the outermost shell. So he could go out and he could steal 7 electrons and that would get him to 8. But that sounds like an awful lot of work. Okay. Well, what happens? Here's his configuration. He's got 1 electron in that highest energy level. What would happen if he got rid of that 1 electron? He gave it away, kicked it to the curb. Well, if he gets rid of this 1 valence electron, gives it away, then that 3rd energy level is no longer needed. It exists, but it doesn't exist anymore, right? There's no electrons in there. So now what's his highest energy level? 2. And how many electrons are in that 2nd energy level? 6, 7, 8. Well, that's happy. That's what he wants, right? So even though he goes down in energy level, that energy level is full and he's happy with that. He's like, cool, that's sweet, man. So of these guys in the first energy level that have one valence electron are going to give that electron away or be okay with it disappearing. Okay? So the purpose of this exercise is to find the nearest noble gas. Just like when you're on an airplane and they say, find the nearest emergency exit, it may be in front of you or it may be behind you. Same thing here. Find the nearest noble gas. It may be in front of you, so you steal electrons to get there. It may be behind you, so you give away electrons to get there. Okay. So everybody in this first family has one valence. It's easier to give away one than to steal 7 and give away 1. What do you think these guys do? So my first question, how many valence electrons do they have? They have 2. They're in group 2A, so 2 valence. To get to 8, what do you think they do? Do you think they steal 6, or do you think they kick 2 to the curb? Yeah, they kick 2 to the curb, right? They give 2 away. So if they give 2 away, they're going to have a charge. There's going to be a charged particle, and it's going to be a positive 2. The silly way that I remember that these guys are positive on this side of the periodic table is if stealing is a bad thing, giving is a good thing. So if I give away my electrons, that's a positive thing. I get a positive charge. Okay. The last group I want to talk about, and this is the group that probably gets missed the most because it's across the bridge here, is these guys in 13 or 3A. But if we slow down and really think it through, it makes a lot of sense. So how many valence electrons do these guys have? 13, 3A. They have 3 valence electrons. Okay. So if they have 3, they want 8. They can either steal 5 or they can give away 3. Yep, giving away 3 is a little bit easier. That's a smaller number. So they're going to give 3 electrons away. Giving is a good thing, so it's going to be a positive 3 charge. Okay. So just an introduction, a brief preview to these charged particles, these charged atoms. We'll talk about them in much more detail in the next chapter, but I like to at least introduce it now and then reinforce it later. So let's move forward into other periodic trends. So the first trend that we talked about was valence electrons, and that led us right into what kind of ions or charged particles do these form. The next thing we're going to talk about are these families. So we talked about them as all having the same number of valence electrons, and having the same number of valence electrons gives them the same properties. So we're going to talk about 4 families here. The first family we've already talked about is this group 18 or 8A. This is our noble gases. So just like people in your family, brothers, sisters, cousins, you guys have a lot of the same characteristics. Same thing with these families or groups in the periodic table. So everybody in this family is going to have the same characteristics. So things like they're relatively stable, right? They have 8 valence electrons. They don't really react with other atoms. They're pretty inert and stable. And everybody wants to be like them. That's the other thing too. The next family we're going to talk about here is our halogens. So halogens are in group 7A or 17. They have 7 valence electrons. And halogens are so close to being like the noble gases that they pretty much react with anything and everything in order to steal that 1 electron and become like the noble gases, stable like the noble gases. So what you'll find is halogens are very reactive chemicals in their elemental form, when they're in their elemental form. All right, let's hop over here to the other side of the periodic table. So our alkali metals and our alkaline earth metals. So again, if you think of this periodic table as being a cylinder, those alkali metals are 1 step away from being like the noble gases. alkaline earth metals are 2 small steps away from being like the noble gases. So what we find is these guys are very, very, very reactive as well. Very unstable, very reactive. They are happy to give that 1 electron away. And when they give that 1 electron away, they do it in very dramatic fashion. So if you don't believe me, Google rubidium in water, potassium in water, sodium in water, and you'll see a pretty fun explosion with any of those. So in their elemental form, they're very unstable. They're ready to give that electron away. And when they do give it away, they do it in dramatic fashion. So just 4 families that you're going to need to know the names for. The next trend we want to talk about is this idea of main group versus transition. And we've talked about this before. So these yellow ones here are our main group elements. Our main group elements behave. Main group elements are very, very predictable. And oftentimes they're the first ones that we talk about in chemistry because we can set rules because they follow the rules. These guys down here in blue are our transition elements or transition metals. Transition elements or metals march to the beat of their own drum. They do not behave. They're always the exception to the rule. We've seen that once already, right? The D block is off by 1 energy level, and that's really just the beginning of how peculiar they behave. One of the reasons that they do behave so oddly is the fact that that D block is kind of in a wonky spot. So that D block is what causes these elements to have extra properties, we'll say. They're a bit extra, these elements. Okay. And then I want to go back to this periodic table because I like it. As you see the numbering system up here at the top. So now that we understand that these are transition elements, these are main groups, there's 2 ways to number the periodic table. The first way is what we see here. It's an A-B way. So if we start here, we go 1A, 2A, hop over to the other main group elements, 3, 4, 5, 6, 7, and 8. And we just kind of ignore the transition metals. And remember, these numbers up here at the top tell us about valence electrons. The other numbering system is just a traditional 1 through 18. So we include the transitions. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 18, right? So again, we can still determine number of valence electrons. Essentially, you're going to put your finger over the number 1, and these guys have 3. And you put your finger over the 1, and these guys have 4, 5, 6, 7, and 8. So 2 different ways that you'll see to number the periodic table. Both serve their own purpose, so both are useful. Okay. And then the last trend I want to talk about before moving on to something a little bit more difficult is this idea of metals, nonmetals, and metalloids. It is absolutely vital for the next chapter that you are able to quickly identify a metal versus a nonmetal. Metals and nonmetals dictate the type of bonding that takes place. So learn it now. We'll utilize it on the next test. So metals are the vast majority of the periodic table. So all of these guys in this kind of tan color here. So the left-hand side of the periodic table. Metals are exactly what you would expect of metals. They're shiny, they're malleable, they can conduct electricity, they can conduct heat. So picture a metal in your mind, and that's the properties that all of these metals have. Over here in this teeny tiny little blue section on the top right-hand side of our periodic table are our nonmetals. So our nonmetals are everything that the metals are not. So they are typically a gas or a liquid at room temperature, do not conduct electricity, do not conduct heat. So they're everything that a metal is not. Even though it seems like a really small portion of the periodic table, don't let it fool you. So the nonmetals have a really, really big chemistry. And that really big chemistry is called organic chemistry. So when we start bonding nonmetals to other nonmetals, we get some really, really large biological molecules. So don't let their small number fool you. They have a really, really big chemistry. And then lastly, we see these metalloids. So this is just kind of green stair step coming down the middle here. Metalloids are just our transition from a metal to a nonmetal. So do they conduct electricity? Yeah, just not really well. Do they conduct heat? Yeah, but not well. So they're typically a solid at room temperature, but they're just a nice transition between a nonmetal and a metal. Okay. So that's it for different groups and properties on the periodic table. Now what I want to do, and this topic is a little bit more difficult, now what I want to do is talk about some properties of the elements themselves. So the three properties we're going to talk about are size, something called ionization energy, and metallic characteristic. So there's some trends inside of the periodic table that we can talk about for these characteristics. So the first characteristic we're going to talk about is size. So when we talk about the size of an atom, what we're talking about is the distance from the nucleus to the edge, the outermost edge. So we're talking about the radius, the atomic radius. So here's just three different pictures that are depicting that fact. So here's our nucleus, here's the outermost edge. So what is the radius of this particular atom? So here is our trend for atomic size. We're going to talk about two trends. We're going to talk about top to bottom. We're going to talk about left to right. So those are two trends that you see pretty quickly here. Top to bottom makes the most sense, so that's what we're going to start with. So let's look at this first family here. So hydrogen down to cesium. What do you notice about atomic size? Yeah, as you go down the periodic table, the atoms get bigger. Well, that should make a lot of sense. So what are we doing as we go down the periodic table? We're adding energy levels, right? So in hydrogen, where are our valence electrons? Well, they're in the 1s orbital. In lithium, where are our valence electrons? 2s. Sodium, third energy level. Potassium, fourth, fifth, and cesium has them in the 6th. So as we stack on these orbitals, one on top of the other, or superimpose them, as we stack these orbitals around the nucleus, of course, those valence electrons are going to get further and further away from the nucleus. So higher in energy, more energy levels, of course, it gets bigger. Okay. But what about this trend left to right? So left to right, it gets smaller. So the reason it gets smaller is something called effective nuclear charge. So I'm just going to summarize and scratch the surface of this. Dive into your textbook and read for more detail. But essentially what happens as we move left to right, so let's look lithium to neon, is the protons that are in our nucleus are reaching out and grabbing onto the valence electrons. In lithium, those protons reach out, they grab the valence electrons, and they pull, P-U-L-L, they pull them a little bit closer to the nucleus. They squeeze them in a little bit. And as we move across the periodic table, and once we finally get to neon, we have the same process. So the protons are reaching out, grabbing those valence electrons. And in neon, they are pulling with a much greater force. So they're squeezing or hugging those electrons closer to the nucleus. And that's why we see the size goes down. So lithium reaches out, pulls it in just a little bit. Neon reaches out and hugs it really, really close, pulls it all the way in. Okay. Then we add an energy level and we squeeze them in. Add an energy level, squeeze them in. Add an energy level, squeeze them in. So left to right, they're pulling those valence electrons closer and closer and closer and closer to the nucleus. How and why are they doing that? It has to do with effective nuclear charge. So go ahead and read that for more detail. But that's the shortened version of what's going on. The next thing your book talks about before it moves out of this idea of atomic size is, well, what happens when we form ions, okay? So I don't love this graphic. I'll show you another one later, but it's the one your textbook gives us, so I'm going to use it. So the first ions that we're looking at here are the positively charged ions. So remember, giving away is a positive thing. So these are the ones that are giving away electrons. And what we see here is the gray is our neutral atom, and the pink here is the ion. So what do we notice when we go from neutral to ion? What happens? Yeah, it gets smaller. And that should make a lot of sense, because what are they doing when they give away that electron? Yeah, they're essentially giving away an energy level. So remember, sodium had 1 electron in the 3rd energy level. He gives it away. Now where are his valence electrons? Yeah, they're only in the 2nd energy level. So that should make sense. They're getting smaller. And then the opposite of this process is the negatively charged electron, or negatively charged ions. So again, we've got gray is neutral, green in this case is charged. Negative, remember, it's bad to steal. So negative is when they grab an extra electron and shove it into their configuration. And it should make sense that those guys bulk up a little bit. If I'm grabbing an electron and I'm shoving it in to my configuration, of course, I'm going to bulk up a little bit. I'm going to get a little bit bigger. So negative ions get bigger. This is the graphic that I like a little bit better. It's still the same thing, but what it's showing here is neutral, positive ion, neutral, positive ion. And if we go to the other side, here's neutral and then the negative, neutral and then the negative. So this graphic and these two depict the exact same thing. How am I going to ask questions about this? So the questions that you'll see are, here is 4 elements. Let me go back to this one. Here's 4 elements. Put them in size range from smallest to biggest, or biggest to smallest. So that's how you'll see these questions. The next trend that we're going to talk about is something called ionization energy. So let's first talk about what ionization energy is, then we'll talk about the trend in it. Ionization energy is the amount of energy required to remove an electron or take away an electron. So I kind of made it sound like when people give electrons away, that's a good thing. Well, it still costs them some energy to give away that electron. So the amount of energy required to get rid of that electron or remove an electron is ionization energy. Okay. Again, we're going to look at 2 trends. We're going to look top to bottom, and we're going to look left to right. Okay. So let's look at top to bottom. So what we see here, top to bottom, is that ionization energy goes down. What does that mean? Something with a high ionization energy means that it's really hard to remove those electrons. So if it's got a high ionization energy, it's holding on to those electrons a little bit stronger. A low ionization energy means it's a little easier to take them off, a little bit easier to remove them. So top to bottom, ionization energy goes down. Well, why does that make sense that it would go down? Well, think about what electrons we're removing. We're removing valence electrons, right? So as we go from top to bottom, why would it be easier to pull an electron off of cesium than it would be hydrogen. Those electrons are further away from the nucleus, right? So there is an interaction between the positively charged protons and those negatively charged electrons. But in cesium, those valence electrons are really far away. So they're less susceptible or more susceptible to be taken away. They have less interaction with those protons. So cesium, because the valence are so far away, a little bit easier to take them off. For hydrogen, those valence electrons are very, very close to the nucleus. So it's going to be harder to take those electrons away from from near the nucleus. Okay. So top to bottom, the valence electrons get further away, a little bit easier to take them away. Now let's look left to right. So ionization energy for lithium, pretty low. Ionization energy for fluorine and neon, pretty high, right? But that again should make sense if we think about valence electrons. So let's think about lithium and fluorine. What's fluorine going to do? Yeah, fluorine's trying to steal electrons, right? He's got 7 valence electrons. He wants to steal one from somebody else. If he's going out and trying to steal electrons from somebody else, do you think he's going to readily give up one of his other 7 valence electrons? You know, he's not. He's not. So he's going to fight to keep them. So his ionization energy is going to be really high. He doesn't want to give up those electrons. What about lithium over here? Well, lithium has 1 valence electron, and he's kind of like, meh, you can take it if you want it. So it's going to be a little bit easier to reach out and grab lithium's valence electron from him than it is fluorine. So lithium's not really going to fight you much. He's just going to say, you know what, pull it off and you can have it. Where fluorine's going to say, you cannot take my valence electrons. I'm trying to steal yours, so you're not taking mine. And then we see these guys here, the noble gases have a really, really high ionization energy, and that also makes sense. They have 8 valence electrons. They are particularly stable. They don't want anyone messing with those electrons. So again, they're going to fight to keep all 8 of those as well. Okay. The last characteristic that we're going to talk about is metallic characteristic. So metallic characteristic, again, we're going to talk left to right, top to bottom. So metallic characteristic left to right, if we think about where metals and nonmetals are, so sodium, magnesium, aluminum to chlorine. So which one's going to have the more metallic characteristic? Aluminum or chlorine? Yeah, aluminum foil, right? Aluminum's a metal. So things on the left-hand side are more metallic. Things on the right-hand side are less metallic. Think about where our nonmetals are. They're over here on the right. So more metallic to less metallic. I don't love the row that they picked. I feel like this row right here is a little bit better of a row. So let me go ahead, just in case you don't have your periodic table out, let me go ahead and write in what elements are here. So we got carbon, silicon, germanium, not that you really know what that is, tin, and lead. Okay. So you guys are probably a little bit more familiar with tin and lead than you are bismuth. So that's why I like to use this one. So if we think about top to bottom, carbon to lead, I think it's getting more metallic or less metallic. Yeah, it's getting more metallic, right? Lead, tin, those are obviously metals. We've seen them before. Carbon is a non-metal, pretty important to sustaining biological life. So as we go top to bottom, it gets more metallic. Okay. So those are the 3 properties I want to talk about. Atomic size, ionization energy, metallic characteristics. And you will for sure be asked a question, something like, here's 4 elements, put them in order from biggest to smallest. or put them in ionization energy from lowest to highest, or metallic characteristic, most metallic to least metallic. And that is just a skill you have to practice. It's something that you are not going to be able to just perform on a test without practicing it. So please make sure you practice that. This is the end of chapter 3. So you should be getting ready to take that next exam. I hope you guys found this helpful.